So Dr. Giada Arney is a NASA postdoctoral program fellow at the NASA Goddard Space Flight Center and a member of the Virtual Planetary Laboratory. She recently received her PhD from the University of Washington, where she worked on photochemical, climate, and spectral simulations of worlds enshrouded by global haze decks. And so this is a really exciting thing about that she's having a chance to study is what these exoplanets are like. And her colleague is Dr. Eddie Schwieterman. He's a NASA postdoctoral program fellow, also with the NASA Astrobiology Institute Alternative Earths team at the University of California, Riverside. He also received his PhD from the University of Washington in Seattle. And he is, his research has included modeling the spectral appearance, climate, and photochemistry of terrestrial exoplanets, which is, of course, what we're really, really looking for. And so we want to find those astrobiology, those biosignatures. And so Eddie and Giada are going to share with us about their work to do that. And so please welcome Drs. Giada Arney and Eddie Schwieterman.
Okay, hi everybody. So I'm going to go ahead
Brian.
and share my screen.
So Giada's just going to load up the presentation, and then we're gonna kind of trade off a little bit as we go, because we're giving this joint presentation and presenting little bits of aspects from both of our works and also a general overview. And so since Brian already gave us that great introduction, I think we can just move to the next slide and kind of outline what we're going to talk about tonight. And so the first thing we're going to do is talk about the state of characterizing exo-Earths, or planets we might expect could be habitable, could be like the Earth. Of course, a lot of it's a perspective investigation, and Giada's going to talk about missions and how we might observe Earth-sized planets orbiting other stars. Then I'm going to talk about biosignatures. What is a biosignature? How might we recognize it on an exoplanet? We're going to talk then about the Earth through time. So the Earth has represented different states throughout its history. It would have looked quite different 2 billion years ago than it does today. And so all of those, we have evidence for that in a geochemical record. And all of those states are, of course, plausible states for Earth-like planets to exist in. So Giada's going to talk about that. I'm going to talk a little bit about potential false positives for life, or how we might be fooled by abiotic processes that could generate what we might think are biosignatures in exoplanet atmospheres, and how we could basically stop that before it happens and rule those scenarios out. And then finally, Giada and I are going to talk about the case of Proxima Centauri b. And this is an incredible discovery. We're so looking forward to learning more about this planet. We don't know a lot about it now, but what we do know is it's the closest it could possibly be for an exoplanet in a habitable zone around another star, and that's just amazing news. And so if you just move to the next slide here, this is why we're talking about it. Potentially habitable planets are being discovered. This is a great graphic produced by the Planetary Habitability Lab, and this sort of gives a little bit of an overview, and with artist conception images of what these planets that have been detected either through transits or radial velocity, what they might look like. So this is a 2-scale a representation of these planets. We know at most their mass and radius. In some cases, we only know their radius or only their mass, and so we have to guess at the other thing. But we're pretty sure that most of these have a rocky composition, likely a secondary outgassed atmosphere, maybe not, but they definitely orbit within a range of distances from their star in which, if they had an appropriate atmosphere, they could maintain liquid water on their surface. And so now that we have this growing list of potentially habitable planets, we really have to start thinking about how we're going to characterize them. And so now I'm just going to drop it off to Giada, who's going to talk about what missions are coming up.
Yeah, so we're in a really exciting time, because not only do we know about these exoplanets now, we're actually starting to find small terrestrial size, so Earth-sized exoplanets, which are obviously really interesting when you want to think about planetary habitability. But just around the corner are missions that are not just going to be able to find these planets and give us really basic information about their properties. Like Eddie was saying, we know their masses, sometimes we know their radii, their distance from their stars, but that's it. And so when you're concerned about, planetary characteristics and just really understanding these planets as unique worlds, we need more information. And so there's a couple missions on the horizon. One that I want to point out is JWST, or the James Webb Space Telescope, which is a 6.5 meter diameter telescope that would mainly be able to take infrared observations. Now, the James Webb Space Telescope will be able to observe exoplanets as they cross in front of their stars. So as the planet, as you have your star, the planet passes in front of the star and blocks out a little bit of that starlight, and the James Webb Space Telescope could potentially measure features in the planet's atmosphere as it looks for absorption of the starlight that's being backlit behind the planet passing through the planet's atmosphere. But these are really hard observations for JWST to make because JWST was not designed for exoplanets. We hardly knew about exoplanets when we started building this telescope. And so at most, if we're lucky, we might be able to characterize one or two transiting, so when it passes in front of the star, Earth-sized planets with JWST. In the more distant future, there's a couple other missions, but the most exciting mission or group of missions to me is what on here is called New Worlds telescopes. There's a lot of different concepts for this telescope. This is a telescope that has not yet really been, it's still in design. There's a couple of different competing designs for what this New Worlds telescope could be. One of the designs that's being worked on is something called HabEx, which is the Habitable Exoplanet Finder, I think it's called. This is a telescope that would be somewhere on the order of 4 to 6.5 meters in diameter, so potentially a little smaller than the James Webb Space Telescope. And it's mainly looking for signs of habitability on a few Earth-sized planets. But the mission that I get really excited about, and the mission that's actually being worked at NASA Goddard, which is where I'm at now, is one called LUVOIR, which stands for the Large UV Optical Infrared Telescope, because astronomers love acronyms. So this would be a really huge telescope, something like 9 to 16 meters in diameter. And this telescope is designed to detect tens of Earth-sized planets in the habitable zones and search for signs of life. And both HabEx and LUVOIR would be looking at reflected light from these planets. So they'd be able to block out the star and directly see the planet. And in order to do that, you need advanced techniques such as things called coronography or star shades, which are occulters that would fly in front of the telescope. And these are challenges because we've never done coronography. We never had to block out something with a contrast ratio as extreme as it is between planets and stars. An Earth-sized planet is about 10 billion times dimmer than its star. And so there's a lot of photons from the star you have to block out in order to see the tiny planet. But fortunately, missions like LUVOIR are quite big. So here's, putting it into context. On the left image on this slide, you can see the telescope had HDST, or the High Definition Space Telescope. That's another name for LUVOIR. And you can see how much bigger it would be than JWST. And on the right side, you can see a simulated image of what an exosolar system, our solar system, might look like from a great distance using this telescope. And of course, observing time with these things is going to be expensive, literally expensive. These are expensive telescopes. But a mission like LUVOIR is potentially designed to be a long-lasting, serviceable telescope that might be operable for something like decades. All right.
Great, and so thanks, Jada, for that. And so this is a segue. Since observing time is going to be so expensive, we really want to know how we're going to recognize a planet that's habitable, and if so, if it's inhabited. And of course, the sooner that we can recognize whether the planet's habitable or inhabited, the more we can spend the time on the interesting targets. Or if we could, for example, rule out the habitability of a planet, we could go to the next target. And so here's just an image of from Cassini of Saturn, and then on the lower right there you can see a pale blue dot. That's Earth. And so this is just sort of to give you perspective that when we're going to be looking at exoplanets, we're not going to have any spatial information about the planet. We're just going to have a pixel of light that's going to be a certain color, but we can unfold the light spectrum from that planet and look at evidence that there's different gaseous molecules there, or maybe evidence for different surface features. So if we can go to the next slide. I just wanted to get through some definitions here. I mentioned habitability and biosignatures, and what I mean by that, of course, is that they're different. Habitability means there's evidence that the planet can or does maintain surface liquid water. That's the definition of habitability that we have. And yes, there are cases where you could imagine some kind of like exo-Europa or something, but those planets, whatever potential biosphere would be there, would be completely unobservable from interstellar distances. So we really take surface liquid water to be the determining factor. Biosignature is a positive indicator of life, so something that life is producing that you would expect to be produced by life. An anti-biosignature is something that maybe shouldn't be there if life is present. Life would, for example, remove it if life was present. And then what I'm going to call a false positive indicator, I'm going to get into that later, is evidence for a process that would abiotically generate something that you would otherwise think is a biosignature. So if you saw that a biosignature and a false positive indicator, that could mean that you don't actually have a real biosignature. So if we could go to the next slide. And so here are the requirements for planetary biosignatures. I said, we're going to be looking at these planets across vast distances. So whatever evidence that life produces to change the composition of the planet's atmosphere or its surface has to be observable over interstellar distances. That means it's probably global in extent, has to produce observable features. So if it's, for example, gas, like oxygen has to interact with light in such a way to create a stamp or a fingerprint that can be observable. It has to build up to a detectable amounts, and it has to be separable from abiotic processes. So that's important. So if you think of a kind of an application form for a biosignature, let's say it's methane, we're going to ask it a few questions. Are you produced by life? Okay, yes, methane is produced by life, bacteria and cows, for example. Okay, let's move on to the next question. Do you have experience with vibro-rotational transition? So this is just a fancy way of saying, can you interact with light? And methane can. Okay, so now we'll move on to a tough question. Have you ever been mistaken for a geological process? And unfortunately, methane fails there. Methane is produced by many geological processes on Earth. It's, for example, it is a major constituent in the moon Titan. We're pretty sure that there is no Earth-like biosphere on Titan. Some of those other abiotic processes include chemical interactions at hydrothermal vents. And so methane alone is present, of course, and also in all the giant planet atmospheres. It's not alone a very good biosignature. So if we go forward, so one approach we can take to this is called an Earth-based approach. And this just means that when we're thinking about biosignatures, we kind of look to the Earth for an example, and there's advantages to that. The Earth-based biosignatures automatically pass the first few tests. We know they're produced by life. We know they're detectable and can build up. We can use existing data and models of the Earth system to sort of explore what they look like, and we'll always have more information about our own planet than any exoplanet, because we have these ground truth values. We have so much richness here on the planet we live on. Okay, so this is just an infographic I put forward about the different types of planetary biosignatures. And you can categorize them basically based on how they'd manifest themselves to an observer. And so I'd start with gaseous biosignatures, which are, as the name suggests, compounds produced by life that can survive in the atmosphere and build up to detectable quantities. And so the big exemplar here is oxygen, which is produced by photosynthesis. So photosynthesis is a process that takes water on the surface and carbon dioxide in the air. It combines it with plentiful photons from the sun to generate biomass, or this is a very simple empirical formula for carbohydrates there, and oxygen as a waste product. And that oxygen as a waste product in our atmosphere over many billions of years has built up to a detectable amount. And there's also byproduct of that oxygen, which is ozone, which is also potentially a detectable gas. It's okay, we can go to the next one. So if your atmosphere is somewhat clear, photons can interact with the surface and get reflected back. And so one example, if life is at the surface, it can interact with that light. And so one example of that is called the vegetation red edge, or VRE. And it's basically this phenomenon that occurs when you look at the wavelength-dependent reflectance of leaves. You notice the green bump, that they're more reflective at green wavelengths than other wavelengths. But what you don't notice with your eyes is that they're very reflective in the infrared, just redder than your eyes can see. And this is actually something that's been used by Earth-observing satellites to map forests and vegetation, farmland on Earth. And conceivably, it could be used to find kind of exovegetation on an exoplanet if you had adequate data and if the surface coverage was significant enough. And then the last thing I'll talk about here is temporal biosignatures. And so you might think there's a gas that's not by itself a biosignature, like carbon dioxide is produced by volcanoes. There's carbon dioxide, of course, a lot on Mars, planets that are not habitable. But there's a geochemical cycle on Earth that recycles that carbon dioxide. There's also an interaction with the biosphere. So in northern hemisphere, during the growing season, the biosphere is sucking up carbon dioxide and reducing it slightly in the atmosphere as biomass builds up. And then as the winter drags on, the biomass dies and it's not sucking up as much CO2. Some of that CO2 is released, and you end up with an increase in CO2. And so that modulation is actually observed on Earth. And if it was big enough and you could get it on an exoplanet, that might also be a biosignature. Okay, and so this kind of analysis was done by the Galileo spacecraft on a gravity assist flyby in the early 90s, and Carl Sagan wrote this up in a Nature paper. And this is, many people have probably heard of this, but if you haven't read it, it's a real treat because he writes it as if he has never visited Earth. And we're going to it for the first time, and we're looking for evidence that there's life there. And so the Galileo spacecraft trained its instruments on Earth and found evidence of oxygen, of methane, of nitrous oxide, which is laughing gas, all compounds produced by life, and seen together establish something called chemical disequilibrium. And so if we just go to the next slide, chemical disequilibrium, next slide, is just the idea that you have two compounds or gases that should just react together immediately or soon within a short time scale. And that's true of methane and oxygen. They should annihilate each other. But the fact that we see both in the atmosphere suggests there's an active source for both of them. So that's a strong biosignature on Earth. And oxygenic photosynthesis, just to mention this again, is a leading biosignature candidate. People talk about it all the time because it is the potentially most energetic metabolism on Earth. It only needs very simple ingredients: water, carbon dioxide, some trace nutrients, and light from the star. And of course, I'm papering over a lot of complicated biochemistry that needs to evolve on that planet also, and geology that needs to occur on the planet for the oxygen to build up. But it is one of the primary things we're going to be looking for. Yeah. Okay, and then besides oxygen, there are other gases that we might look for. I've listed some here, sulfur compounds, methyl chloride, methyl mercaptan, ethane. These are some biosignature gases that may be seen, some of them seen alone might not be quite evidence for life, but seen with other things might be evidence, and some alone would be very intriguing. And so this is just to say that there are many different gases besides oxygen we might look for. And if we go to the next slide, we can just see that this is just a graph that shows you the gases that are emitted to Earth's atmosphere with life, that's the left side, and without life on the right side. And you can see all these gases would have much different fluxes in the atmosphere without a biosphere present. Of course, this doesn't include the actual absorption features of all of these gases, and that create some complications, but we wouldn't expect an exoplanet with a biosphere to necessarily be exactly like the Earth. So we've got to keep an open mind for all these other gases too. And then finally, you can kind of look at habitability markers in the same way. You might tell whether the planet is habitable. The fact that you don't find a biosignature doesn't necessarily mean it's not inhabited, that there's no life, but it might just mean that you got unlucky. But we just certainly would like to know if the planet is habitable. We'd want to look for water vapor in the atmosphere. We'd want to look for a nitrogen and carbon dioxide that show there could be a sufficient greenhouse effect. SO2 could be an indicator of volcanism. Surface features could tell us directly there's liquid water if we can observe the glint effect from the ocean. Surface heterogeneity implies continents and oceans, and that could be very intriguing. We want there to be clouds, and if there are variable clouds, that's great. And so here is a model, but this is a pretty well-validated spectrum of the Earth from the visible all the way through the thermal infrared. And so you can see here, and again, this is the brightness of the planet as a function of wavelength. Okay, and so the blue, in the blue square is the reflected light, and in the red square is the emitted light. The light the Earth is emitted because it's hot. It has a temperature. And you can see that there are signatures from ozone, that's O3, and oxygen, O2. There's that lambda to the -4 is Rayleigh scattering effect. That's why we have a blue sky, and also why the Earth is blue from a distance, as I showed you in that Cassini photo. And we can see evidence of both CO2 and methane as well. Okay, so I'm going to turn it over to Jada now.
All right, so obviously the sort of holy grail for exoplanet science is we want to find Earth-like planets. But I think when we think about Earth-like planets, it's an interesting notion, because a lot of the time when we talk about finding Earth-like planets, we're talking about finding planets like modern-day Earth, right? We want to find planets that, you know, have Earth-like atmospheres with oxygen and nitrogen and, you know, trace amounts of methane and CO2 in them, just like modern-day Earth. But Earth through time, which you're seeing here, so this is a sort of pie chart that shows the different epochs of Earth's history, has looked very, very different compared to modern day Earth. So you can see the box at the top, right? Like that's now, that's humans. If we go back into the past, say to the Proterozoic, there were no large, you know, macroscopic life forms on our planet through the Proterozoic. So that's a huge chunk of Earth's history. And then if we go even farther back into the Archean, which ended at about 2.5 billion years ago. In the Archean, as well as in the Hadean, there was very, very little oxygen in our planet's atmosphere. And as Eddie was just telling you, oxygen is sort of this canonical biosignature that we're searching for. But oxygen didn't even start to build up in our atmosphere to detectable quantities until about 2.5 billion years ago, at the start of the Proterozoic, during something called the Great Oxygenation Event. So when we think about what an Earth-like planet spectrum looks like, and we think about modern-day Earth, if we rewind the clock and go back through time, you know, Earth is going to look very, very different in these different epochs. And so this slide is just to sort of illustrate different sort of cartoon images of the Earth through time. And what I've spent a lot of my time doing research on, and a big part of my PhD dissertation involved looking at Archean Earth, which was, again, sort of that pink part of the pie chart. So between about 3.8 and 2.5 billion years ago. Archean Earth would have been a very different world compared to modern day Earth. It would have had a lot fewer continents compared to modern day Earth. And a big thing in the atmosphere is that, like I said, it would have had an anoxic atmosphere, because even though there was oxygenic photosynthesis operating during the Archean, the oxygen in the atmosphere hadn't yet built up to large quantities. So there were many orders of magnitude less oxygen in the Archean compared to modern day Earth. And because oxygen and methane react together and they want to destroy each other, an interesting thing about the Archean is because you don't have the oxygen in it, you could have orders of magnitude more methane in that planet's atmosphere than you could in the modern day atmosphere. So methane in Archean Earth's atmosphere would be a lot more detectable compared to the modern day atmosphere. And an interesting thing about methane-rich atmospheres is that if you had a ratio in the atmosphere of methane to CO2 greater than about 0.1 or 0.2, which is a lot more methane than we have today, you can actually trigger the formation of a global organic haze, similar to the haze that's in Titan's atmosphere. An analogy I like to use for what this haze is sort of qualitatively like is photochemical smog. So if you've ever been to LA or any other large cities on a day where there's not a lot of atmospheric circulation, you probably have seen smog, sitting low on the horizons close to the cities. So imagine this smog lofted tens of kilometers up in the atmosphere and enshrouding the whole planet, and it would be a sort of orange color. And this is what Earth may have looked like for some periods in the Archean. The entire Archean would not have been hazy, but we do have geochemical evidence suggesting that this haze existed at some times in the Archean. So here's a picture of hazy early Earth next to Saturn's moon Titan, which has a similar organic haze in its atmosphere. Now, as Annie was mentioning, methane is interesting, but it's also really slippery to deal with because methane can be produced by both biological and geological processes. So the biological process that produces most of the methane in Earth's atmosphere and is called methanogenesis. Now, methanogenesis is a really simple metabolism. It uses really simple stuff like H2 and CO2. It's a metabolism that evolved really, really early on. We have evidence of it in the geochemical record dating back to about 3.5 billion years ago, and it likely evolved earlier than that. So it's possible that similar simple methane-producing metabolisms could evolve on Earth like exoplanets. But of course, methane can also be produced by geological processes, as Eddie mentioned. And the dominant geological process that produces methane on Earth is something called serpentinization, which occurs at the seafloor, and it's when water hydrates certain types of rocks at the seafloor. And one of the byproducts of the chemical reaction that occurs is the release of methane. And so serpentinization is itself interesting because it's a process that requires liquid water, which is a sign of habitability on a planet. And so because the dominant sources of methane on Earth-like planets are either life or this serpentinization process that needs liquid water, I think methane is a really interesting gas to detect because it signals some really interesting things that could be going on that planet. So, we're looking for these pale blue dots right now. So if you can imagine you're a little purple alien and you're looking through your giant 16-meter telescope at an exoplanet and you see it's a pale blue dot, you might get really excited because you might think, oh, this is a planet like the one I live on. This is an Earth-like planet. But what if it looks like something else? What if it's a pale orange dot? Like what if it's an Archean Earth analog planet with a haze in its atmosphere? Would we be able to recognize that planet as quote unquote Earth-like and correctly deduce that it might have habitable conditions and possibly life on it? So I've thought a lot about this question, doing a lot of modeling with different climate and photochemical models to generate atmospheric states for hazy early Earth. And I've generated also spectra of what the remote observables of hazy early Earth would look like. So I'm going to show you some reflection spectra of what this planet might look like from a distance with a haze in its atmosphere. Okay, so here are these reflectance spectra of Earth with 3 different haze thicknesses in its atmosphere. So the black spectrum that you see here is a planet with no haze in the atmosphere, and this is an Archean spectrum, so it lacks oxygen and ozone that our modern day spectrum has, and it has a lot more methane and CO2. The blue spectrum is a spectrum with a thin haze, what I call a thin haze in it, and the orange spectrum is what I call a thick haze spectrum. And I've also labeled some gaseous absorption features, so you can see where methane and water vapor absorb in this spectrum. You can see there's a lot of methane absorbing in this spectrum. And a thing to notice, right, is there's a huge, just sort of qualitative morphological difference between the spectrum with no haze and the spectrum, especially with the thick haze. And that's because the haze absorbs this blue light very, very readily. So these short wavelengths, these blue and UV wavelengths, you can see that the reflectivity on the y-axis for these hazy planets is really, really down for the thick haze planet because the haze is such a good blue and UV absorber. This blue absorbing propensity of these haze particles is the reason why Titan is orange, and the reason why early Earth, if it had a haze in its atmosphere, it would also be orange. And a cool thing about this feature, right, you can see it's a really, really strong, broad feature here, is that it's even stronger than the spectral features for methane itself. And so it's potentially an indirect way of detecting methane in a planet's atmosphere if you don't have access to the methane spectral bands themselves. This is the kind of spectrum that, say, LUVOIR or HABEX might be able to collect. So if you can directly image an exoplanet and detect its reflected light. But with something like the James Webb Space Telescope, you're actually going to be observing the planet in transit transmission when it passes in front of the star. So between you and between the star and the telescope, it'd be directly in the middle of it, and the starlight would be passing through the edges of the planet. So the planet would be backlit by the star. So what I'm showing you here are some transit transmission spectra. The y-axis here is showing you the altitude that the light from the star can get down to into these planets' atmospheres before it's absorbed. So notice how at these shorter wavelengths for the thick K spectrum, for example, if you look at, say, 0.4 microns, that the light can only get to about 80 kilometers into the planet's atmosphere above the planet's surface. Whereas in the no haze spectrum, the light can get much, much deeper down into the atmosphere, somewhere around, say, 30 kilometers at 0.4 microns. And you've got this very strong spectral slope in the thick K spectrum where, right, you can see much more shallowly into the atmosphere at short wavelengths compared to longer wavelengths where you can see deeper into the atmosphere. So this slope is a characteristic of these organic hazes. And so if we see similar exoplanets that have these very sloped transit transmission spectra, where their planet is much more opaque at shorter wavelengths compared to longer wavelengths, because again, these organic hazes are much more absorptive at these short UV and blue wavelengths compared to longer wavelengths where they're much more transparent, so light can penetrate deeper down, that would be a strong indicator that you have an organic haze in the atmosphere, as well as if you saw these methane bands. So you can see here these methane absorption features in these spectra, which are these bumps you see in the spectrum. And the reason why they appear as bumps here is because when you have an opaque molecule in the planet's atmosphere, you're not going to see as deeply into the planet's atmosphere. If you look at it at a wavelength where methane absorbs, you might say only see down to 40 kilometers, versus if you look at the place where the methane is not absorbing, you might see much more deeply. So that's why the absorption features are bumps here. And so with the James Webb Space Telescope, we can actually go out to much more longer wavelengths. So before I was showing you out to 1.6 microns, which is in the near infrared. But the James Webb Space Telescope is designed to study infrared astronomy. So it could go out to potentially much longer wavelengths. Now, the problem with getting to these much longer wavelengths is that the star itself gets much, much dimmer at these longer wavelengths. And so your signal to noise drops off very, very steeply as you push farther and farther into the infrared. And in practice, you probably couldn't take observations of exoplanets at wavelengths longer than 10 microns. But I do want to point out that there's a feature at about 6 microns that you can see labeled there, haze. So that is an absorption feature that you see as that bump in the orange spectrum compared to the other two spectra. And that feature is due to the haze itself. And so this would be potentially another way of directing organic haze in a planet's atmosphere. Now, organic haze, again, it's interesting because methane itself is interesting. Methane can signal these fascinating processes like biological processes and also serpentinization, this process that needs liquid water in order to produce methane from geology. And so how on earth would we figure out what's going on these planets? So this complicated contour plot, I promise is not that complicated, is showing how we might start to disentangle what's going on if we see an organic haze in a planet's atmosphere. So the color bar is showing you sort of optical depth of the haze. So how thick is the haze? How much is it actually affecting your spectrum? The y-axis is the amount of CO2 in the planet's atmosphere. The more CO2 you have in general, the more difficult it is to form a haze and the more methane you need to form that haze. And the x-axis is the flux of methane at the planet's surface that's going into the atmosphere. And then the solid line with the zeros is where you have an optical depth of unity. So this is a log plot, so log of 0 is 1. So that's where you have optically thick haze. Now, in the Archean, we think the amount of CO2 in the atmosphere was somewhere in the range of this box. And what we find is that for Archean-like CO2 levels, you need methane flux rates on the order of about somewhere around 10 to the 11-ish molecules per centimeter squared per second being produced at the surface in order to have enough methane in that planet's atmosphere to form a thick haze that's going to strongly impact your planet's spectrum. And this is actually really interesting because for these thick hazes, this is consistent with the production of methane by biology on Earth. And so if you saw a thick haze and simultaneously were able to measure the amount of CO2 in a planet's atmosphere, you could argue that you need a methane production rate that's at least consistent with known biological methane production rates on Earth. And it's higher than known abiotic methane production rates on Earth. So on Earth today, the production rate of methane from abiotic processes like serpentinization is 1 to 2 orders of magnitude lower than the biological production rate. Now, of course, this isn't a smoking gun because on an exoplanet, we don't know what the abiotic production rate is. And of course, we also don't know what the biological production rate is. But again, at least we could say that, using these sort of photochemical, geochemical constraints that we infer from what our own planet does, that organic haze in the presence of high CO2 could indicate methane production rates that are consistent with biology, even if we can't say it's biology for sure. And then we'd start to stare at the planet harder to try to see other signs of habitability. Like, does it have water? Does it have other biosignatures? Does it have these sort of temporal and surface biosignatures that Eddie was mentioning earlier? And that could start to, sort of nail down the question of what exactly we're looking at. And again, these hazes are cool because they have such a strong, really great detectable spectral feature. All right, so back to Eddie now.
Okay, thanks. And I might move through this section just a little bit quickly because we're running low on time. But I'm going to talk about possible false positives for life, so how we might be fooled by what we might think are biosignatures, but in reality are results of abiotic processes. So if we go to the next slide, sort of the conclusion at the beginning of this, beginning of the millennium, was that there are only a very narrow set of circumstances where you could produce oxygen, which again is a very interesting biosignature because it's produced by photosynthesis. This range of conditions is very narrow, and that primarily would occur in regions outside of the solar system. It might occur inside the inner edge because you're so hot you're evaporating all your water, and your water goes into your upper atmosphere, and the hydrogen is cleaved off that water by UV radiation and escapes, potentially leaves that oxygen behind. And so when the first papers about the runaway greenhouse came out, they sort of talked about this possibility, why it didn't happen on Venus, and if Venus potentially had more water, it could have had an oxygen atmosphere. And then there have been papers on the outer edge of the habitable zone, and how if you had a ice-covered surface, you can't react your photochemical products. So again, cleaving oxygen off of CO2 or water, you couldn't react that with the surface as it happens on Mars, where the oxygen that's liberated from those reactions gets combined with the surface, which is why it's rusty. But if you were prevented from doing that, you might build up some oxygen in the atmosphere. So if we go to the next slide. But recently, there have been many more potential difficulties here because there have been all these other proposals for how this might happen inside the habitable zone. And so if we just go to the next slide and talk about specifically O2 from CO2 photolysis, which is probably one of the most easy of these mechanisms to understand. And if we go to the next slide. So this is just saying, if you can just click, yeah. So we're just highlighting this reaction here. CO2 plus a photon, that's H nu, goes to CO plus O, cleaving an oxygen off of a CO2 molecule, and those oxygen atoms can recombine into a oxygen molecule. Now, this process is strongly disfavored on the Earth, and in fact, almost all of our oxygens from photosynthesis, this process is very ineffective. But if we just look at some spectra for different stars and advance here, we can see that different stars have different UV spectra. And so then they drive this reaction in different ways. And so while it's true that this reaction and this process for building up oxygen is strongly disfavored on a planet around a sun-like star, it's actually more favored on planets orbiting different kinds of stars. So if we go to the next slide, this is just sort of showing the strength of the UV ozone band, the Hartley-Hurley bands on the left side there. The left upper corner is reflected light as Jada kind of illustrated, the difference between reflected light and transmitted light. So the upper left is ozone and reflected light. The bottom left is ozone and transmitted light. The upper right is oxygen in reflected light, and then the bottom right is oxygen in transmitted light. And you can see the strength of these features. So this is all assuming, this is using a photochemical model and assuming that no biotic process is going on, just the photochemical reactions in the atmosphere, assuming different spectral types, that you would end up with potentially detectable amounts of oxygen for certain types of stars. And so that's a good thing to know. We go next. But there's going to be what I called before a false positive indicator here, in the sense that while you're cleaving off these oxygen atoms from your CO2 molecule, and then those later can become oxygen molecules, you're also generating a lot of CO, and that CO could potentially be detectable. So on the left hand side here is just a simulated spectrum of this process happening. So it's self-consistent with the photochemical model, and then we've pretended that JWST is observing this planet transiting another star where this process is favored, and we're calculating what it might see. And so you can see that both the CO2, if we advance here, the CO2 is visible, and then if we advance again, we can see that the CO also produces bands. Now, this is actually more observable than the oxygen itself. So if you saw this for a planet, it might tell you that this is a planet where an abiotic process is going on. It's generating potentially abiotic oxygen, and so you shouldn't be fooled by that. If we go advance here, so there are other methods for doing that. One is, if we advance again, just this concept that if you lack a substantial enough atmosphere, you're not going to cold trap your water like Earth's water is cold trapped. So most of our water clings close to the surface. It doesn't go all the way up into the atmosphere because there's enough other air around that makes that process disfavored. But if you remove a substantial amount of nitrogen, for example, from our atmosphere, and if we didn't have oxygen from photosynthesis, then you could potentially put your water into the upper atmosphere and have the same UV reaction happen where you cleave off oxygen from water and potentially generate oxygen. That would generate itself enough to self-limit, again, and cold trap the water. So that's an equilibrium state where you have almost as much oxygen as we do on Earth abiotically. But again, if we advance, the way to rule this out is to directly detect nitrogen. And so we've kind of demonstrated that for the Earth, at least, we can detect nitrogen in our spectrum and in the spectrum, and it would be enough to rule this process out. And if we go forward again, the final thing is a little bit more complicated to understand, but it's this fact that for stars that are significantly dimmer than our sun, they have a very bright pre-main sequence phase. And so they're much brighter as the planets are forming. And that means that they're much more liable to lose their atmospheres, including the hydrogen that would have been part of the water. And so if we go forward, for M stars especially, this is a big problem. They could lose a lot of water in the beginning of their history. That also leaves behind a lot of oxygen. Now that oxygen could react with the surface, or it could build up in the atmosphere. Now, if that happened, if we advance, the question is just distinguishing a lot of oxygen, some oxygen from a lot of oxygen. In the whole history of the planet Earth, we've had at most 0.3 bars of oxygen. And this graph sort of shows that. If we go forward again, there are signs of what are called O4 bands, which are when two oxygen molecules combine or collide, they generate an observable signature. And so we could look for that. That would show that there's a massive oxygen atmosphere that's too massive to just be from photosynthetic life. So if we go forward, this is just, again, an example of what JWST would see in that circumstance. If you had a very high, massive oxygen atmosphere and you looked at it in transmission, you would see these O4 bands come up. And that's a very big counter indicator for photosynthetic life. And if we go forward again, we can also see this in reflected light. The black spectrum is sort of an Earth-like atmosphere, and then the other bands are more massive atmospheres. And so wanted to get a little bit in on Proxima Centauri so we can go forward. And so, okay, so this one, just to say that there are things to look for that would rule out these false positives. And if we could find them, or rule them in or rule them out, and if we could find them, then we could be much more confident about our designation that that oxygen came from biology. So if we go forward, we can talk about Proxima for a bit.
All right. So we've probably heard of Proxima Centauri b. It was announced in August, and it is an Earth-sized planet in the habitable zone of the closest star. So what a jackpot! Super exciting. It was discovered with the radial velocity method. So you're measuring the Doppler shift of the light from the star as the star wobbles from the planet circling around it and giving the star little tiny tugs. And so this method allows you to measure the planet's mass and also its distance from the star. And again, that's about it. We know very little about this planet. But just because it's in the habitable zone and just because it could be habitable, it doesn't mean it actually is. We don't have the knowledge yet to be able to say what exactly Proxima Centauri b is. But what we can start to do is think about whether or not we can actually discriminate between different atmospheric states. This planet could be a lot of different types of things, so we need to start anticipating what the spectral observables of those states are so that we can start to build the instrumentation and data reduction pipelines that we need in order to characterize this thing in the future.
Okay, so one possibility is just like I described. Proxima is a very late type star. It's an M-type star, and it was much brighter in its early history than it is now. And so that means that Proxima Centauri probably lost a lot of water. And if it did, then it has this capacity to potentially, according to recent studies, build up oxygen. So if we just advance, as I sort of showed before, this would produce observable signatures that would let us know that that oxygen could not have been from biology and was primordial from this early history of the star. And so that's the main point of this slide.
Okay, so what if it's like early Earth with a haze or perhaps without a haze? So I ran our photochemical climate model to simulate Archean type atmospheres, both without a haze and with a haze. And not all stars are able to form a haze. However, Proxima Centauri does have the right amount of UV radiation to form a haze. And so if there's a haze on this planet, we'll be able to see it because it'll produce a whopping big spectral signature.
And if it's like modern Earth, there are some complications and actually exciting aspects of this. So the fluxes into the atmosphere from biology is one part of the equation, but also how those gases, what their lifetimes are and what their abundances are is dependent on the incident spectrum. So we found when modeling photochemically an Earth-like atmosphere is that you would actually have a lot of buildup of methane, which is really good news because you would have both detectable oxygen and detectable methane. So methane is strongly favored to build up on Proxima Centauri if it had sort of an Earth-like atmosphere to begin with. So if we advance the slide, you can just see how clear this is. So the only difference here is one set of lines is the spectrum of the Earth-Sun and one is Earth-Proxima. And you can see these big differences due to different methane bands. And so we assume the same flux of methane into the atmosphere. The photochemical lifetimes are just very, very different. And that allows for methane to potentially build up to really high quantities in Proxima.
All right, so we want to actually, figure out how observable is this thing going to be with future instrumentation. What you're looking at on this slide is a modern-day Earth analog planet orbiting Proxima Centauri, because of course that's what we would love for it to be, as observed by a LUVOIR simulator. The solid colored lines you see are IWAs, or inner working angles, and they are different. So the coronagraph that is used to nullify the starlight, to block out the starlight, has a wavelength-dependent behavior, and its ability to block out the starlight sort of falls off a cliff at what's called the inner working angle, after which you see the star again, and you can't see the planet again because it's totally outshined by the star. And so these are sort of wavelength cutoffs for how good the IWA could be. We don't know what the IWA is going to be for any future instrumentation, so these are just different assumptions of what it could be. Ideally, you'd want something like the green line. That would be the best because that'd give you the biggest spectrum and the most spectral information, but it could be something like the red line, which would cut you off at like 1 micron, which would give you a lot less information. You'd see a lot fewer, say, methane bands. You wouldn't be able to see CO2 anymore. And also notice that you actually get pretty good signal to noise. So these are error bars on the plots, and notice how the error bars are pretty small in the near infrared, just because Proxima Cen emits most of its light in the near infrared because it's quite a red star. But in the visible region, there are larger error bars. HabEx is a smaller telescope, and the IWAs for smaller telescopes are a lot smaller. So unfortunately, HabEx would have a much more difficult time characterizing this. The best case scenario for a smaller telescope like HabEx is that it might be able to get out to a little bit beyond 1.1 microns. So here, LUVOIR, you can see, gets out to something like almost 3 microns with the most optimistic IWA. So you're losing a lot of information. And more realistically, we'd probably be dealing with an IWA of something like lambda over 2 lambda over d, which is the blue line, which you can see really does not get you much information. You can see Rayleigh scattering, but that's about it, sadly. Do you want to do this one, Eddie?
Well, I kind of want to just leave these up so that we can talk about questions, but this is just a cool plot put together by one of our colleagues that shows the color of the planet orbiting Proxima Centauri if it had an Earth-like atmosphere. So you're combining the red light from Proxima with the sort of the blue Rayleigh scattering from Earth, and you get sort of a purple lavender color. And then if you had a hazy Archean Earth, it'd be this color.
Pink.
Pink. So I think this is a great time for questions. And so maybe I can just answer the first one. So I'll answer the have there been any studies of what non-carbon based life forms might look like and what its biosignatures might look like. And so that's an intriguing question. The thing is, we don't actually even know what non-carbon based life forms, what their biochemistry is even like. And so if we don't know what their biochemistry is like, we don't necessarily know what gases they put in the atmosphere, and therefore what we should look for in the exoplanet atmosphere. I will say that there have been studies in what life would look like on Titan, and there's been some progress in thinking about what a membrane would look like to exist in that cold liquid hydrocarbon solvent. It's called an azosome, and it's made artificially in the lab. And so there's a little bit of progress there, but we're kind of looking at this Earth-based strategy right now, just because that's what we know best.
All right, it looks like there's another question or comment. It looks like that Mars is also orange without haze, and yeah, it is, because iron oxide is another strongly blue absorbing thing. In fact, iron oxide is, you can almost sort of think of it as a false positive for haze because it has a similar spectral behavior. The difference there is Mars's atmosphere is a lot more a lot less reducing than a methane-rich atmosphere would be. So when we're dealing with these exoplanets, right, we need a lot of spectral contextual information to figure out what we're looking at. So ideally, what you want to see is that haze signature, that blue UV absorption combined with methane bands. And that would really clue you in on the fact that you're actually looking at haze and you're not looking at something else like iron oxide absorption. All right.
Yeah, it looks like we've got a question coming in. They couldn't quite get to the Q&A. It looks like Miklos would like to know a little bit more about the background spectrum and how it can be subtracted to study the signal.
Background spectrum. Could we get a little more information about that question?
I think it's about how you're isolating the spectrum from the planet from the star, which is much brighter, and so maybe a little bit more about the techniques to isolate. Remove the starlight.
Yeah, so I think you might be asking about how are we going to see the tiny little firefly next to the giant floodlight that is the star, where the firefly is the sun. We're working on that. We don't have the technology yet that can do that, but there's 2 different techniques that are being studied. One is a coronagraph. A coronagraph is an internal occulter that lives inside the telescope to sort of mask inside the telescope that is designed to block out the starlight. So it's designed to block out the light that would be hitting the center of the aperture. So you position the telescope such that the star's light hits the center of the aperture, and you put some sort of mask there. This is difficult. We don't yet have coronagraphs that can perform at the level of precision that you need to, remove all the photons from the star except 1 in every 10 billion that you need to see the planet. But there is a lot of people actively working on this problem right now. And then the second one is a starshade, which is an external occulter. So this would be something that would fly outside of the telescope, and it would position itself between the star and the telescope at a pretty large distance. Like, I don't want to make up a number, but like thousands of kilometers or more distance from the telescope. And this is something that, again, blocks out the starlight, so it would hide the field of view from the center. So you block out the starlight that way. Okay,
great. Well, it looks like we have time for, we have one last question that came in. And this is an interesting question. Jeff asked, will good candidates with reasonable biosignatures for habitability be sent radio hello messages? Are we going to say hello to the potential bios?
Yeah, okay, I'll answer that. So we've been focusing on biosignatures, sort of the microbial biosignatures, so how life interacts with the atmosphere. And we kind of look at sort of SETI signals as technosignatures. And one of the reasons that that we kind of separate that, it's not that we don't think SETI is a bad idea, we think it's a great idea. It's just a very different set of expertise needed to characterize an exoplanet atmosphere versus detect a radio signal from a ETI civilization. I will say this: if we look at that history of life on Earth plot that Jada had up earlier, I don't know if she can go back to it.
Probably, yeah.
But basically, the history of life on Earth is 4.5 billion years, and for a substantial amount of that time, microbial life was interacting with the atmosphere and potentially generating an observable signature in the atmosphere. And only like 0.000000001% of the time was there a communicable civilization generating radio signals. So my opinion is that ET is a microbe, and it's trying to contact us through the changes it makes to its planet's atmosphere.
All right. Well, it looks like we're right at the top of the hour, about a minute past. And so, Jada, if you'd like to, go ahead and stop sharing your screen. And so then we can wrap things up. I want to thank you very much. This is really fascinating, this whole idea about being able to figure out what atmospheres are like of all these exoplanets. It's very exciting. I think it's great. So basically, that's going to be it for tonight. You'll be able to find this webinar along with many others on the Night Sky Network under the Outreach Resources section, just for the webinar. We'll post tonight's presentation on the Night Sky Network YouTube page by the end of the week, where you can also find some other videos from past webinars as well.